We've sent probes to every corner of our solar system, to the Sun, to Jupiter, even beyond the orbit of Neptune. But two destinations still remain almost unreachable: Pluto and Proxima Centauri. Pluto is an icy world on the edge of sunlight, and Proxima Centauri is a star so far away that even light takes years to reach it. The problem isn't just distance, it's physics itself. To achieve these goals, you have to go faster than anything humanity has ever created, and then, somehow, stop. That's why, even after decades of progress, both worlds remain elusive, symbols of how vast the universe is and how small we remain in it. For decades, Pluto was an unattainable dream, a cold, silent frontier at the edge of the Sun's domain, more than 4 billion miles from Earth. It lies so far away that even light takes hours to travel the distance. In the 20th century, even imagining a mission, there was like planning a trip into eternity. And yet, humanity tried. In the early 1970s, NASA engineers discovered a rare celestial opportunity. Between 1976 and 1978, for years, the outer planets Jupiter, Saturn, Uranus, and Neptune were supposed to align in a way that only happens once every 176 years. With perfect timing, a single spacecraft could use their gravity like a slingshot, zipping through the solar system and saving decades of travel. This project was called the Grand Tour and was supposed to include Pluto. The mission design was brilliant. 4 spacecraft visiting all the major planets in one continuous flight. But the cost was astronomical. When NASA canceled the Grand Tour due to its prohibitive cost, only 2 smaller probes survived, those that would later become Voyager 1 and Voyager 2. Pluto was still in the plans at first. NASA even considered sending Voyager 1 to it after Saturn. But a last-minute decision changed everything. The scientists chose to redirect the spacecraft to Titan, Saturn's largest moon, a world with a thick atmosphere and the potential for life. It was a scientifically sound decision, but it permanently eliminated Pluto from the mission. From that point on, Pluto became a planet that kept slipping away. Throughout the 1980s and 1990s, new proposals. Smaller, faster probes could reach Pluto before its fragile atmosphere froze as it moved farther from the Sun. But each time, budgets were cut, priorities changed, and time ran out. It was too far, too slow, and too expensive. Even solar energy was useless there. The sunlight was only a faint echo. Any mission to Pluto would require radioisotope generators, nuclear power. And even then, the energy would be very limited. But a few scientists refused to give up. Among them was Dr. Alan Stern, a planetary scientist who had led the fight for decades. He insisted that Pluto was not just a frozen point, but a full-fledged world, one that could hold secrets about the origins of the solar system. His persistence eventually paid off. In 2001, NASA approved the New Horizons mission, a small nuclear-powered spacecraft designed with the sole purpose of reaching Pluto before it was too late, launched on January 19, 2006. New Horizons became one of the fastest objects ever created by mankind, reaching speeds of over 30,000 km, 49,000 km/h. Even at that speed, the journey took 9 to 12 years. When the spacecraft finally arrived on July 14, 2015, it didn't stop. It couldn't. New Horizons flew past Pluto just once, making a high-speed flyby and capturing the first and only close-up images of this distant world. For days, humanity gazed at what had once seemed impossible: glaciers of nitrogen ice, blue hazes, and a heart-shaped plain carved in frost. But even in the moment of triumph, the truth remained the same. The hardest thing was not to reach Pluto. The hardest thing was to stop there. When New Horizons flew past Pluto in 2015, it didn't slow down and couldn't. This fact explains why reaching Pluto and even more distant worlds is so deceptively difficult. It's not just about getting there, it's about stopping once you get there. In space, speed is survival. To overcome Earth's gravity, a spacecraft must accelerate to at least 11 kilometers per second. To reach the outer planets, you need even greater speed, tens of thousands of kilometers per second. But the further the spacecraft goes, the faster it has to go so that the journey doesn't take centuries. And every kilometer per second gained along the way must be compensated for if the spacecraft wants to slow down. That's the paradox. The faster you go, the harder it is to stop. When New Horizons left Earth, it was designed for only one flyby. It had neither the fuel nor the propulsion system needed to reach Pluto's orbit. That would require an additional rocket stage nearly as massive as the spacecraft itself, as well as decades of additional flight time. At 4 billion miles from the Sun, there is so little light that solar panels can barely power a light bulb, and the chemical fuel used to reach orbit near the planets becomes useless when it has to slow down from 30,000 to port in near weightlessness to be captured by Pluto's gravity. The spacecraft would need an engine capable of operating continuously for months, and a colossal supply of fuel. Even a minimal maneuver at that distance requires incredible energy. Every extra gram of mass adds years to the mission. So instead of trying to stop, New Horizons simply flew by, gathering the maximum amount of data it had in the few hours it had, traveling at incredible speeds. And it is this very problem that makes Proxima Centauri even more unreachable. If the flight to Pluto took 9 years at record speeds, imagine traveling to the nearest star over 4.24 light-years, or about 40 trillion kilometers, at the speed of Voyager 1, humanity's fastest interstellar probe. Such a journey would take about 76,000 years, and even if we could accelerate to a fraction of the speed of light, we would face the same dilemma. How do you stop when you arrive? A spacecraft traveling at 10,000 kilometers per second, just 3% of the speed of light, carries the kinetic energy equivalent to thousands of nuclear bombs. To slow down at such speeds, you need propulsion systems that are far superior to our current technology. Nuclear engines, ion tractors, even advanced plasma drives could cut the travel time to Proxima Centauri by thousands to centuries, but that's still not enough for human life. And every increase in speed makes the braking problem many times more difficult. In interstellar space, you can't just turn around and fire up your engines. It would take as much energy to stop as it did to start. And most of that fuel would have to be injected from the ground. In other words, the faster you want to go, the heavier the ship becomes, and the harder it is to get it moving at all. That's why missions like Voyager and New Horizons never slow down. They're designed to drift forever. Carrying human curiosity into the darkness, they can break free from the sun's gravity, but not from their own momentum. On the scale of the cosmos, we have taken only the tiniest step. We have learned to hurl our machines into the void, but we have not yet learned to gently stop them near another star. For now, Pluto marks the limit of where we can go, and Proxima Centauri remains the limit of what we can only dream of. Humanity's path to the stars has always been limited by one word: thrust. Every leap forward from the Moon to Pluto has been determined by how fast we can accelerate and how efficiently we can decelerate. But to go beyond the solar system, we need to rethink motion itself. Today, the spacecraft we launch still rely on chemical propulsion. the same basic principle that has been used since the 1960s. It is powerful, but incredibly inefficient for deep space. To reach even 1% of the speed of light using chemical fuel, a probe would need a tank with a mass greater than the mass of the entire Earth. This is absurd. That is why scientists began to dream differently. One such dream was ion engines, which eject charged particles at enormous speeds. They are slow to start, but in the vacuum of space, they can operate for months or even years, gradually gaining speed. Missions like Dawn have proven their reliability in the outer reaches of the solar system. But even these futuristic engines would take tens of thousands of years to reach Proxima Centauri. Then came Vasmer, a plasma engine designed by former astronaut Franklin "Chunk" Diaz. Using magnetic fields to accelerate ionized gas, it promises trips to Mars in little more than a month. Theoretically, it could cut interplanetary travel times by a factor of 10, but even an ideal Vasmer would take more than 2,000 years to get to Proxima Centauri. And then came a radical twist: laser sails. Instead of waiting for the sun, we could use ground-based laser arrays to propel the sail to incredible speeds. Thus was born the breakthrough StarSat concept. The plan was to send swarms of microprobes, each the size of a dime, to Alpha Centauri at 20% of the speed of light. The journey would take only 20 to 30 years. It is bold, dangerous, and perhaps the first real step towards interstellar travel in our lifetimes. But there is one problem. Even at such speeds, the probes will not stop. They will whiz past Proxima in a matter of seconds, capture everything possible, and disappear into eternity. The truth remains. We have mastered the art of leaving home, but we have not yet mastered the science of arriving. For centuries, humanity has stared into the night sky and perceived distance as a challenge, something to be overcome. From Galileo's first telescopes to the workings of the eyes that roam the darkness today, our question has always been the same. How far can we go? But now, standing on the edge of what has been achieved, the answer is humble. We can go far, but not far enough. Pluto and Proxima Centauri have become two cosmic mirrors, one on the icy edge of sunlight, the other near a distant star. And between them lies the same obstacle: the rigid mathematics of distance and energy. And Proxima Centauri taunts us from beyond our reach. Only 4.24 light-years, our nearest neighbor, and yet unreachably distant. At our maximum speed, a probe would take longer to reach it than all of human history. Even if we could build ships capable of crossing this chasm, we would still be haunted by the same problem as New Horizons: uncontrolled speed, no return. Every proposed solution, fusion engines, nuclear pulses, solar sails, runs up against the same cosmic truth. Space is incredibly vast. Every extra meter per second requires energy on a scale that is beyond practicality. And even if we could solve the problem of thrust, communication would break, navigation would fail, and the time delays between now and then would stretch for decades. The deeper you go into space, the lonelier you become. That's why missions like Breakthrough Starshot are so important. Tiny ships, lighter than a sheet of paper, accelerated by laser light. A fleet of 1,000 eyes sent into the void. They may not slow down, they may not survive the journey, but they represent something more important than success: intention, the human need to move forward, even when the destination is out of reach. Because that's what exploration by faith has always been. When we sent Voyager, we knew it would never return. When we launched New Horizons, we knew it would never stop. And if we ever send a mission to Proxima, We know it won't come back to tell us what it found. But that's never stopped us. Each of these journeys is not just about science. They are about who we are. To go beyond, to reach for the impossible, is to challenge the limitations of our biology. We are creatures of gravity, bound to one small world. But our minds refuse to stay here. We build machines as extensions of ourselves, to see, to touch, to travel where we ourselves cannot. And perhaps, in a century, one of these machines will slow down. It will orbit another star and send back images not of home, but of another home. A pale speck revolving around a dim red sun where human history begins anew. And until then, Pluto will remind us of how far we have come, and Proxima Centauri of how far we still have to go. In between lies the truth of our age. We are explorers, locked in the slowest century of discovery, standing at the dawn of a space age that we can almost touch. And so we keep moving. Every launch, every failed mission, every scrap of data from a fading probe, all carry the same message to the star. We are here, we are trying, and even if we are not yet able to cross the interstellar gap, every light we chase brings us one step closer to what we are destined to become. Because after all, the journey to Pluto showed us that far is just a word, and the journey to Proxima will decide whether it is impossible or not, only by its different meaning. There is something eerie about the way our greatest missions end. Voyager still whispers from the darkness nearly half a century later. New Horizons drifts past Pluto, chasing sunlight it will never again feel. And perhaps one day, so will the sails of the starships, humanity's tiny messengers, gliding silently between the stars. Each of these probes is more than metal. They are echoes of who we are, dreamers, engineers, explorers. Every signal they send is the heartbeat of the Earth, a reminder that curiosity is our oldest instinct, because the further we travel, the more we understand the cosmos. It is not just a destination. It is a mirror that shows what we are capable of becoming. When New Horizons discovered the frozen heart of Pluto, it was not just science, it was a symbol. At the edge of the solar system, the heart still beats, and beyond it lies Proxima Centauri, our nearest neighbor and our greatest temptation. 4 light years, a distance that defines the true meaning of the word impossible. And yet we keep trying. We design faster engines, lighter sails, bolder missions, not because we expect quick success, but because hope itself demands movement. And perhaps that is the secret of our species. We are icy but relentless, limited but unafraid of infinity. Someday, our descendants will look back and see these first attempts, Voyager, Pioneer, New Horizons, as the first flashes of the cosmic dawn. They will say that this is when humanity began to expand its horizons, because exploration was never about escaping home. It was always about rethinking it. So we move on, past the icy plains of Pluto, past the fading light of our sun, and into the unknown between the stars. Not because it is easy, nor even because it is logical, but because wonder demands it. And in this pursuit, in this endless pull forward, we discover the rarest of all, ourselves. And if you could choose only one direction, which would you visit first? The frozen heart of Pluto or the unknown world of Proxima Centauri? Write your choice and the reason in the comments below. Like this video if it made you think about how far we can go.